I am Dr. Anjutama, Associate Professor in Physics, MSJ College, Bharatpur. The topic which we are going to discuss for MSc classes today is conducting sphere with hemispheres at different potentials. So in the last video in LM-18, we found that the potential phi of x is equal to 1 over 4 pi integration phi a theta dash phi dash a into x square minus a square divided by x square plus a square minus twice ax cos gamma raised to power 3 by 2 d omega dash. So that was the article in green function for the sphere, general solution for the potential, where we got this potential phi of x as we have written here it as an equation 1. So as an example of the solution given by equation 1 for the potential outside a sphere with prescribed values of potential on its surface, we consider the conducting sphere of radius a made up of two hemispheres separated by a small insulating ring. So let me draw it like this. So I have this. Just a minute. So let me use this here. Okay. And yes. So I have to let it be the insulated ring. So x, y and z. So the hemispheres are kept at different potentials. The upper hemisphere is at plus V potential and the lower is at minus V potential. So these hemispheres are kept at different potentials. Now let us consider the potentials as plus minus V. And since the arbitrary potentials can be handled by superposition of the solution for a sphere at fixed potential over its whole surface, this insulating ring lies in the z equal to 0 plane. The insulating ring lies into z equal to 0 plane as we have shown in the diagram, and the upper hemisphere is at potential plus V and the lower hemisphere is at potential minus V. So from this equation 1, the solution for phi x theta phi is given by the integral solution for phi x theta pi. So it can be given by this integral phi x theta phi will be equal to V over 4 pi, and this is integration from 0 to 2 pi d phi dash, and this is 0 to 1 d cos theta dash minus integration from minus 1 to 0 d cos theta dash, and here I have this, it will not come here, so let me write it here, a into x square minus a square divided by a square plus x square minus twice a x cos of gamma raised to power 3 by 2. So this is equation 2 here. So by suitable change of variables in the second integral from theta dash to pi minus theta dash and phi dash plus pi, this equation 2 becomes this is phi x theta phi equal to VA x square minus a square divided by 4 pi and integration 0 to 2 pi d phi dash, and this is 0 to 1 d of cos theta dash, and let me write it as a square plus x square minus twice a x cos of gamma raised to power 3 by 2, and this is minus a square plus x square plus 2ax cos of gamma raised to power, it is minus 3 by 2 minus 3 by 2, and this is square bracket closed here. Okay, so this is equation 3. So we get equation 3 here. Now because of the complicated dependence of cos gamma on the angles theta dash phi dash and theta and phi, this equation 3 cannot be integrated in closed form. So as a special case, we consider the potential on the positive z-axis. So as a special case, we are considering the potential on the positive z-axis. In that case, cos gamma, which is cos theta dash, since theta is equal to 0, so cos gamma is simply equal to cos theta dash. The integration is elementary and the potential can be shown to be, in this particular case, the potential just becomes phi z 1 minus z square minus a square divided by z under root of z square plus a square, equation 4. So this is the special case. We are considering the potential on the positive z-axis, so that because of theta equal to 0, cos gamma is just reduces to cos theta dash, and by integration, solving the integration, the potential just comes out to be phi of z is equal to v into 1 minus z square minus a square over denominator z into under root of z square plus a square. Now at z equal to a, this just reduces to phi is equal to v at z equal to a. it will just reduce phi equal to v as is required. However, for large distances, it asymptotically goes to approximately phi equals 3va square over twice z square.